on, we'll be doing project number 7, research your topic. The purpose is to support his points with specific facts and examples. He will be speaking for 5 to 7 minutes. He has a varied background. He has a biochemistry degree and a master's in business. His hobbies are mountain biking and swimming. And like I said, he holds a degree and has a fascination for physics and chemistry. He enjoys finding new ways to explain complexities of those subjects so everyone can understand. Have you ever been camping using a propane stove and noticed the canister icing up? The explanation for that is found in ideal gas law of physics. To hear more, please help me welcome Derrek with supercritical fluid extraction. Welcome, Derrek.
I bet you can't say that 3 times really fast.
Thank you, Mr. Toastmaster, fellow Toastmasters, and guests. Coffee is the number 2 most widely drank beverage in the world, behind tea. Now, have you all ever been in the local grocery store shopping for your coffee and pondered, why do I have the 2 choices between regular and decaffeinated coffee? There's many little things like that in our world that we take for granted, that are actually the result of physics, chemistry, and human ingenuity. And decaffeinated coffee is one of those things. It really should make us go, wow, and not just from the caffeine, but because a cool process called supercritical fluid extraction is involved. And actually, 2013 marked the 50th anniversary of this process. So it's a fairly new process recently developed. Now, decaffeination of coffee is separating the caffeine from all the good stuff, the aromas, the flavor. There's actually 1,000 elements and chemicals in coffee that make coffee coffee. So you're trying to separate those 2. You separate it using a solvent. Now let's step back to your high school science class. And what is a solvent? A solvent is a substance that can dissolve or bind another substance and bring it into a solution. So your coffee, your green coffee beans, has those chemicals, the coffee, the flavor. You're running a solvent through it. The solvent will bind the caffeine, bring it into a solution, and now it's in the solution, you can wash it off, and your coffee beans are left without the caffeine. You have a good picture of the solvent? Now, what do you use as a solvent? Well, decaffeinated coffee was first developed in 1905 by a guy called Ludwig Roselius. He was a German coffee merchant. Back in 1905, he had benzene at his disposal. So he used benzene as the solvent.
Whoa.
Now in modern day, they use methyl chloride or ethyl acetate or charcoal, activated charcoal. Now a lot of those, they're scary names because, I mean, they are scary. In large doses, they are carcinogenic and toxic. Now the problem with solvent extraction in your coffee beans is at the end, you want to have it all washed off. Well, there's always a residual amount left there. Just think of when you take a shower. There's always some soap somewhere left on your body. You just can't wash it all off. The same thing with coffee beans. You can't wash all the solvent off. And when you're talking something about benzene or methyl chloride, it's important to wash it all off. So next step into CO2 as a solvent. Not just any CO2, but supercritical CO2. What makes it supercritical? Well, let's think about the state of matter. Matter, back in high school science class, has three phases: the gas, the liquid, the solid. I'm going to draw a little picture here. You have two axes. You have pressure on this side, temperature on this side, and imagine you're raising your temperature as you come across here, raising your pressure as you go up here. So you start here, you have a solid, you have a gas. At some point, there'll be a triple point where you start having a liquid. So you have your three phases there. Well, you keep raising your pressure, keep raising your temperature. This line goes, this goes. You hit another point. And then it kind of does something like this. And then you hit this zone. That zone is called a supercritical zone. Why is that special? That's special because the properties of the gas in the liquid state of matter is ambiguous. The state of matter has properties both of a liquid and a gas at the same time. That is fascinating. Why is it important for your coffee beans? So CO2 can get into the coffee beans, acts like a gas, so it can diffuse all throughout the membranes of the caffeine. But once it's in there, it acts like a liquid, and it dissolves the caffeine into that. And then you can pump it out, bring your CO2 back to atmospheric pressure. It goes to its normal state, which is a gas. Your caffeine can't stay in a gaseous state. It crystallizes out. And you're left with coffee beans that don't have your caffeine, but still have all those good flavors, aromas that make coffee coffee. This process of supercritical fluid extraction was developed by a guy called Kurt Zossel. And this process, it's only 50 years old, like I mentioned. And it's a very cool process because it is able to selectively pull out different compounds. And it's not just used in the decaffeination process of coffee, but it's also used in essential oils that are all the craze right now. You can actually separate out cholesterol from butter. And in preparation for the speech, I found an article about a company using supercritical fluids to apply micro layers of material onto electronic chips. That's fascinating. So next time you stroll down your grocery store aisle, I hope you'll look at your decaffeinated coffee in a little bit different light. Maybe 7 o'clock tonight when you're sitting down having your cup, you'll not just enjoy your coffee, but you have a supercritical eye for your decaffeinated coffee.